Welcome, folks, to this another Cancha tutorial. Today we're going to talk about the regression diagnostics tools that we have in the new version 1.6. I'm going to be using the Bonnie dataset today and give you some ideas on how to diagnose those models that are generated. So without further ado, let's get into Cancha. Here we've got the Bonnie project, and we'll go to the targets area. In the targets area, we're going to create a new target. We're going to do that by pressing this plus sign here and pulling in the results from the metallurgical data set. So let's pull in, for example, cyanide consumption. And here we can see that we've got all of our features here, the possible predictors have been loaded in. The green ones are ones that have come from lookups from geological things like rock type, for example, or alteration logging. Hit play. And so what it's doing now is going through all those different features and trying to find the best possible models and domaining systems. The results are in, and now we can see that the global models up here on subtable 1 have got 20 samples versus 19 in subtable 2. Means that some of the data was missing from that one, so it only had one of the samples didn't have the complete data, so it could only run the regressions on 19 of the samples. Here it ran on all 20. And now when we click on this model here, which is the recommended one, you can see here on the right that it's basically cyanide consumption is being recommended that it's 2.6 times the gold grade minus 0.7. That gives us an R squared of about 0.65. And because it doesn't really have any competing models, it found that it was the best one, so the parsimony scores are quite good, and it's only one parameter. So far, so good. Now, you can see here on the right that in the metallurgical samples table, this has been modified, and now it's got the sample name, it's got the cyanide consumption, which is the target, and it's got the predictor, which is gold. So if we were to click on a different one, for example, this one, where cyanide soluble copper and gold with predictors, we can see we've got cyanide soluble copper and gold, as well as the cyanide, which is the consumption, which is the target for the 20 samples. If we go down in a subdomain with less samples, something with only 5 samples, you only get 5 samples here. And what we can do is we can click on this list, and you can see here, and I'll just bring up in 3D. So here in this 3D window here in the corner, you can see that as we click on the list here in the metallurgical samples, or if we click on the graphs here in the target area, it'll go ahead and highlight it in 3D and also highlight it on the metallurgical samples list. So you can very quickly move between these 3 different areas. You can look at where things are on the regression analysis. You can see exactly what the sample was, and you can also see it in 3D. And if you wanted, you could also hit this button here, and it'll take you to the sample in logs. Okay, so heading back to the targets. Let's go for one with a bit more data. So here we are with this one. For example, we've got 2 parameters, which is kind of nice: cyanide soluble copper and gold. Not saying that this is better than the recommended one, just an interesting one for this exercise. It only has an R squared of 0.37, but what we can see is that we're predicting the cyanide consumption based on these 2 parameters, and we actually do get quite a good predicted versus experimental graph. But when we're plotting these together, you'd say, well, this one's a bit of an outlier. This one seems fine. These are all fine here, but this one's probably the problem here. Okay. Well, that's how we used to do it, and we used to get ourselves in trouble. Now we've learned about how to use a Williams plot, leverage, and standardized residuals in order to diagnose this stuff better. So let's have a look at these regression diagnostic tools. How do they work? Well, first of all, you have to get the idea of the outliers. So an outlier, you can see, is got that red dot there, which is significantly different from the population. It's outside the norm, outside of the confidence range of the rest of the data along the regression. So it's considered to be an outlier. Now, in a Williams plot, that turns up on the top left-hand quadrant. Okay, so that's where the outliers live. Leverage is something different. Here you can see the red dot on the graph on the left. So when we've plotted the data of the target versus the predictors, we can see that we've got a cloud of data that's not necessarily oriented in any particular slope, but when we put one red dot far away, that's got a lot of leverage. If that red dot was to move, the slope of the line would move with it. If it was to come down, the slope would be less. If it was to go, further to the left, then the slope would be higher. Basically, that point is determining pretty much all of the slope on the line of regression. So that's considered to have high leverage. So when it's on the right-hand side of the vertical line there on the Williams plot, we consider that it has too high a leverage, and that could be a danger. Then you've got hostile aliens. I had to come up with a name for this top right-hand quadrant, leverage and outliers. So basically, they shouldn't be there, and they're also mistreating your regression. So what does that mean? Well, you can see now I've changed a little bit the graph on the left. The gray dots are sort of oriented so that there is a natural regression to those points. It's heading up on a higher slope. But the red dot has still got a lot of leverage, so it puts the regression line, the blue line, goes closer to the red dot. So the small slope, because all the other gray dots are tightly packed together, they have lower leverage, and the red dot has high leverage. But also, it's an outlier with respect to the gray dot natural sort of trend there. So you can see there in the Williams plot on the right, it occupies the top right-hand quadrant, which is the worst quadrant. That's considered to be the bad quadrant. Okay, so if data's up there, it's both an outlier and it's got high leverage. So if the data's in the bottom left, that's good. Keep calm, carry on. If it's an outlier in the top left, then you have to check your quality of the data. It could be that the laboratory's done something there. It could be the sample is contaminated. It could be any one of a number of things, but it's sort of data that doesn't really belong to that data set. The data on the right-hand side, the leverage, means that you've got to increase the data density in that area. The data density means basically that you've got too fewer points that are having too much influence because they're occupying part of the regression that they don't have any neighbors. So let's take a practical example of that. So in this case, for example, let's say we've only got one sample that's got high gold grade, and it's causing, and it's associated with a very high cyanide consumption. Then it could be that we need to find more samples of high grade gold samples, and if we have more samples in that area, then it's taking the leverage away from that one point. It means that the regression is backed up by those other points. It could also mean that there's a hidden separate domain. Maybe because it's so separate and it doesn't have many neighbors, could mean that just have to separate it off as a separate domain. Okay, and if it's stuff in the top right-hand corner, the bad area, that's just dangerous. If something's going on there, you've got data with very high grade by itself. That doesn't make any sense. So be really careful with that one, mate. There's another tool in there called the Mahalanobis plot, and it's a little bit easier to understand, a bit more intuitive. Basically, the stuff to the left is good, and the stuff to the right is bad. The distance that it talks about isn't a physical distance. It's not a physical distance in geometrical terms. It's a eigenvalue distance, and it tells you basically when things are far away from each other in different planes, then they probably aren't going to be members of the same domain or the same population. An example might be, for example, where you've got a project that's looking at flotation and there's a lot of dependence on pyrite grade, and maybe you find that a sample's got a whole bunch of iron, and so it should be behaving a certain way, but it's not behaving that way. What's going on? And when you look at it, the sulfur grades are low, and the iron grades are very high, and the flotation response is low, for example. So what might be happening? You might have magnetite instead of pyrite. Okay, so because it's different on multivariate parameters, because it's on different, in different eigenspace dimensions, it's proving that it's got a high distance on multiple variables. That's probably data that should be excluded from that population. Okay, so going back to let's go back into Cancha here, and we'll just take up the 3D. And so here we are back in Cancha, and now you understand the Williams plot. You now know that these points here have high leverage. And sure enough, when I click on this one here, you can see these two do have high leverage. This one has high leverage for gold, and you can see that there's a natural trend here in the gold versus cyanide consumption here. There's a natural trend, and this one is both an outlier, so it's up quite high to the line, and it also has high leverage. It's pulling the graph down this way. This one, less intuitive. It's got high leverage, but you never had to thunk it. Look at this. On the parity plot, actually seems to behave itself quite well. But when we look at it here, on the cyanide soluble copper versus cyanide consumption total, you can see that it's way off by itself. It's a very high value. You can see it's got 1,300 ppm of copper cyanide soluble, which is a long way away from the rest of it. And sure enough, on the Mahalanobis plot, bit of a distant point here. But this point here is by far the worst one. It's distant because it's got high cyanide consumption at a low cyanide copper cyanide value. It's got a high gold grade compared to the rest of it, and so that gives us it puts it over the 97.5% line. And once it's over this line, it really is pretty much a data point that you should be excluding. Okay. So these are dangerous, these points here, and you can look at those. And of course, if we were to have the second screen on the 3D, we click on these and see where they're from. And as you can see, when I'm clicking on these points, which are all outliers, we can see they're all from the same neighborhood. So basically, we're saying that there's a high gold point that has, here, this point here is a high gold value. Okay, it's the highest gold value, and it's the worst point. So here, Cancha has given us the possibility of looking maybe at a gold domaining situation where maybe we could split off this high gold as a separate domain where we've got 3 samples, and they would have higher cyanide consumption, and it's gone ahead and predicted that maybe we could have a model for that based on arsenic possibly, or something, or just use a constant maybe. Okay, but then the gold and median, they possibly combined. You might want to run a Fisher and maybe just go into your legend editor, combine these 2 ranges, okay, and say, well, what if we combine these 2? How would that be? Would that be one single population? Okay. We can actually do that really quickly in Cancha. Just go to legend analysis, and we'll just put in here the put in the cyanide consumption as a feature, and then we'll put in the gold grade as the group by, and then gold grade as the color, and then we'll just go ahead and do Fisher grouping, and sure enough, Fisher says that we should group these 2 together, and the third one, the higher group, is a separate domain. If we wanted to do that, we could just go ahead and add a legend. Right now it's cut off at 2.8 grams a ton, so we'll just reduce that to 2, make this 2.8, apply that. So now if we go back in here again and run this, they get this new target of cyanide consumption. Just wait a couple of seconds, and what comes out? So basically on the gold, now we've got the medium and low, and sure enough, we've got these 2 separated. 17 samples in the low grade one, in a very tight range, and only 3 samples in this high grade group here. So that gives us a way of isolating the high cyanide consumption material. Well, there you go, guys. That's the regression diagnostic tools in Cancha in a nutshell. I hope you've enjoyed it, and I hope you get good use out of it when you're diagnosing your regressions. Any questions at all, just get in contact with us. Always happy to hear from the users. Okay, thanks guys, bye.